Okay, this is Deb, and I'm going to walk you through a little bit of chemistry that might really help because this chemistry chapter is pretty abstract. Biology is based on these principles of chemistry and physics. No matter what happened, if you smell a smell in the room, it's really because that molecule connected with a site in your nostril that then had a chemical reaction and caused you to smell that smell. Brain chemistry, you eat chocolate, it releases a certain type of chemical in your brain that makes you feel good. So we all are really just a whole bunch of chemical reactions, and we're made of matter, anything that contains mass and occupies space. So examples, matter is anything and everything. That's you, everything around you, everything you can touch, everything you see, even the air you're breathing, all of that has mass and takes up space. Some has more mass than others, but it all takes up space. An element is a substance that can't be broken down anymore. So if you look at your periodic table, those are all the elements. Calcium is calcium, can't be broken down. Carbon is carbon, hydrogen, lithium, all those things can't be broken down any further. That's their purest form. A compound is when some of those atoms come together in special ratios, and it creates something different. Like when two hydrogen join a water, join an oxygen, we've got water, H2O. When you exhale, you're exhaling carbon dioxide, which is CO2. Which is one carbon and two oxygens. And so a compound is something we'll see more of in a few minutes. So we already covered this. The atoms are the smallest functional units of matter and form everything. And so what we're going to talk about is a very generalized diagram. The nucleus contains the neutrons, which are neutral, no charge, and the protons, which are positive charged, very dense. Then the electrons swirling around outside are negative charges. And when we have an unreacted neutral atom, that means we have the same number of positive charges in the nucleus as electrons, negative charges swirling around. We'll get into that in a bit more detail. All right, here's a more involved one. We're not going to go there. We don't need to talk about quarks. If you know all about them, good. It's pretty cool stuff, but not what we need. Just generally, I want to explain that electrons, we're going to talk about them in shells, and we're going to act like they stay there, but they don't. They really swarm crazily. And from this diagram here, this blue part is for one hydrogen atom that has one electron. There's where you're more likely going to find the electron. They move so fast, they create solidness to things. It's really, when you touch something, you're touching those electrons that are speeding along. They can circle the Earth in less than 20 seconds. Crazy. So size-wise, the atom size, if you put 1 million together, that's about the density of a thickness of one page of paper. The nucleus density, if you had a penny and it was the same density of an atom nucleus, it would weigh 30 million tons. In relationship of size, if you think about a professional football field and you put a grain of sand at the center at the 50-yard line, that is the nucleus. Then the first shell of electrons doesn't start until you're in the very top row of seats. So that gives you, there's a lot of space in there that those electrons are filling up. And so we're going to talk about the periodic table of the elements a fair amount and use it. So look in your book and pull up that page. I have to come back to that because I had it open, but I shouldn't think. All right. So you'll find the periodic table, and we're going to talk about the shells. The orbit's where you're going to find them, but shells are, we're going to pretend they stay there so we can talk about them. And I'm going to explain to you this handy-dandy way to use this to magically, and so you can figure out how many shells of electrons everything has and how many electrons are in the last shell, which determine how it's going to react. Very, very important. Those electrons in the last shell determine the reactivity of everything. So we've got nucleus with neutron and proton. Hydrogen just has a proton, and then we got the electrons. And I talked about this a little bit, the charges, where they're found, and their mass. We got that covered. Hopefully you found your periodic table on page 21 in your text. First, let's talk about the atomic number. That's the number of protons in an atom. And if you look at carbon, C, it has a 6. Carbon always is 6, and if it has 6 protons in it, it's carbon. F is 9, that's fluorine. It has 9. Its atomic number is 9, and that means it has 9 protons in an atom. However, there's another number there that changes. You'll look on here and see carbon is, the bigger number is 12.01. We round that off when we list it like this for the mass number because that really represents protons plus neutrons, but really it turns out it's the average of the isotopes of carbon. That means they have different atomic masses. So carbon 12 only has 6 protons and 6 neutrons. Carbon 14 has 6 protons and 8 neutrons to add up to 14 total in that nucleus. We'll do some more examples of that. So isotopes just have different numbers of neutrons. Atomic mass unit is what we talk, or Daltons, and that mass number we were talking about represents protons plus neutrons in that nucleus. So we have the same picture again, and here's a mass as 12, 6, and so to figure out neutrons, you just subtract 6 from the 12, and you get 6. So this one has 6 neutrons. This one has 6 protons, but more neutrons. 1, 2, 3, 4, 5, 6, 7, 8. 8 plus the 6, 8, 9, 10, 11, 12, 13, 14 equals that 14 number right there. So we've got your periodic table ready. Let's talk about how magic that is and how it will help you. But first we need to talk about how those electrons fill that shell, because we've been talking about the protons but not the electrons yet. So let's look at the electrons. We've got 1 positive charge, so we've got 1 negative. 2 positive charges, 2 protons, then 2 electrons, and so forth. Now, this illustrates something pretty darn cool that will help you solve all those problems really easily. This group number at the top, that is how many electrons each of these guys in this column have in the last shell. So they've got 1, 2, 3, 4, 5, 6. Boom, 6. Sulfur, 1, 2, 3, 4, 5, 6 in the last shell. Why is the last shell important? That's what determines the reactivity of this molecule, or this atom. And so the last shell, how many electrons are in there, is everything, and it determines how this thing is going to react. So you have a quick thing. You know, these guys all have full outer shells, so they don't want to react with anything, actually. They don't care. They're called the inert gases. 7 here. This guy is pretty darn strong. This guy's going to steal and transfer an electron from something else because it's got 7 and it wants to have 8. Remember that 8 octet rule? It wants to have full. And so these guys in this one are going to do it. Oops, sorry. And so fluorine, very reactive. Chlorine, Clorox, bleach. We're talking about stuff that is very reactive here because they only need 1 electron to fill their outer shell. This end, let's look at these guys that only have 1. They can't hold on to that so well, so it ends up going over to somebody else. So these numbers across the top are the numbers of electrons in the last shell, and then going down, except for helium, there's only 2 because this first shell is full at 2. But when you go down the periods, this is the number of shells they have. So all these guys only have 1 electron shell. These all have 2, so the first one's full, and then the second one. These have 3. The first one's full, the second one's full, and then the third one is the one that has this number in it. So to make that even a little bit more confusing, there's some very weird way this is talked about. Valence. Valence means the number of electrons in the outer shell. Write it down. Valence just means that number that I told you that's across the periodic table. That's the number of electrons in the last shell. Oxygen has 6. All right, valence number means how many electrons it needs to create an octet and to be full. So valence is the number of electrons in the outer shell. You can look and see what group an element is in, and you'll see the group number is the same as that number. Valence number means the number of electrons it needs to be full, to make that octet, which on everything except the first shell is 8. So here's another example. This has 11 protons, so you can look at your chart and see it's sodium, Na, number 11. And let's double check. It looks like it should have, it's right here, it has 1, 2, 3 shells of electrons, 1, 2, 3, and it has 1 in its last shell. Boom, there it is, 1 in its last shell. The first one's full, the second one's full with 8, and then this one guy right here. So the valence is 1, that's how many it needs, and the valence number, if it's going to react with anything but itself, is going to be 7, which is kind of cut off there, sorry. Going to react with itself, it's going to be full with 2. That's hydrogen gas. All right, let's look at how these things hook together then. So here we have chlorine, and if you look at your chart, it's number 17. So it's going to have 17 negative charges around here, and that adds up to 2 in the first shell, 8 in the next one, and if you look, it's in group 7, so it's got 1, 2, 3, 4, 5, 6, 7 electrons in that last shell. That's that stuff that's going to be so reactive, and it's going to actually steal the electron from this one, this hydrogen, who's only got 1. That's going to make an ionic bond. That's otherwise known as hydrochloric acid, very strong. It's a stomach acid that breaks your food down. And here it is again. I put it with the thing. So you see chlorine, 7 is last shell, hydrogen, 1. Boom. Chlorine gets 8. They're happy. Here's methane gas, as a matter of fact. And so carbon has 4 in its last shell. There's carbons. Oh, here's its first shell. It's got 1 shell and 2 shells. So the first one's full, and the second shell is 1, 2, 3, 4. And it wants to have 8, that octet rule. And if we only have hydrogen available that has 1, then we need 4 hydrogens. So they'll fill it in like this. And that's CH4. And you can see that now carbon has 1, 2, 3, 4, 5, 6, 7, 8 in its last shell. That's what it's shooting for. Then there's this thing called CHNOPS that helps you know which elements make up the most of living matter. The first 4 make up 96%. Carbon, hydrogen, nitrogen, oxygen, and then comes phosphorus and sulfur. CHNOPS, a good thing to remember, that life is made up of these 4 elements. Why? And here's some more information about them, how much of human body mass and all that business. Oh, I didn't have a picture in there, but why is because they are very reactive. They have room to add more electrons, and so they react. All right. Let's go through trace elements a little bit. We also need iron. Oh, here's CHNOPS again. And you'll see that we need 4 here, we need 3 here, we need 2 here, and 1 more there. So that makes them really react often and well. So when they react, they make a molecule, and chemical bonds involve the giving, taking, or sharing of electrons. So they're going to give it away, take it from somebody else, or share it. Covalent bond is the sharing of pairs of electrons. Sharing of electrons, yes it does, but it actually shares pairs of electrons. And so we have oxygen. They both have 6 in their last shell. If you look at they're number 8, and so you'll see that they have 6 electrons in their last shell. Well, turns out they can share 2 pairs and make a double bond. So covalent bonds are the strongest bonds. They're the hardest to break. We have 2 types where they're shared equally is nonpolar. And if one has more electronegativity, which means it have more electrons than the other one, they may form a polar covalent bond. And water is a perfect example of that. And we'll talk about how magic water is later. In this PowerPoint, I'm also going to attach in the class, you can watch a bonding animation there as well. Then the other kind of bonds are ionic bonds. They are very strong and happen quickly if you think of strong as quickly, but they break easily. They dissociate in water into the ions really, really quickly. So let's talk about what's happening here. This guy only has 1 electron in its last shell. This happens to be, if it has just 3 electrons, it only has 3 protons, so it's lithium, Li. And this guy over here has 2, 3, 4, 5, 6, 7, 8, 9. So that's number 9, which is fluorine. And it has 2 shells and 7 in the last shell. Well, this has got a lot more electronegativity over here. So what flat steals that electron off of this guy? He can't hold on to it. And now this one has 3 protons and only 2 electrons. 3 positive charges, 2 negative charges. So this is called a cation and has an overall charge that's positive. This guy stole an extra electron, negative charge, so it has an extra negative charge, and so this is an anion, and it has an extra negative charge. Now, these stick together, not because they're sharing anything, but because this one's got a negative charge and this has a positive, and that's what attracts. All right, salt is the perfect example, and salt is wonderful stuff that then builds those little crystals together by atoms in a very cubical fashion. This is what's happening in there with the sodium and the chloride. Very, very, very cool. And what happens when you put salt in water? It dissolves. You don't see it anymore. All of these ions come apart because they're not that strong, and so a negative chloride ion is floating around by itself, and a positive sodium is floating around by itself. This guy lost an electron, this one's got an extra one. And this is how it's formed. Same thing we were talking about. And then let's talk a few minutes about carbon. We are a carbon-based planet. Carbon is awesome. Carbon has 4 electrons in the last shell. That means it can do a whole bunch of stuff. That makes it very important for life. It can form single covalent bonds. It can do double bonds like I showed you in the oxygen gas. Sorry, my thing is cut off. It can do triple bonds like in nitrogen gas. Here's a single bond going on. It can bond with 4 different atoms. It can form chains. It can form branches. It can form rings. It can form, as I said, single, double, and triple bonds. And that is why we're a carbon-based planet, because of that reactivity. Let's talk about, briefly, I see I have a couple minutes left, so radioactive isotopes. We use these guys that have different numbers of protons. Those are the isotopes. So same number of protons, these are the 3 isotopes of hydrogen. 1 proton, but it has different numbers of neutrons. We know that they decay at a certain rate. And since those bits are falling off are radioactive and can damage our DNA, we protect ourselves with lead and all this business. But we use those tracers very, very carefully in things like thyroid scans, nuclear medicine. It's slightly reactive. It doesn't last more than 24 hours. It's got a very short half-life, but it will light up places in the body that there's a lot of activity going on. Obviously looking for disease or cancer. A PET scan puts together a nuclear medicine with a CT. So they're really looking at some pretty amazing things. Here's someone with lymphoma in the chest. The heart is always big, because it always takes up a whole bunch of stuff. But otherwise, these are the tumors going on up there. A PET scan can show Parkinson's disease. It shows functions going on in there. Normal Parkinson's, and this is pre and post treatment. Alzheimer's. Guess which one is? This one's Alzheimer's. This one's normal. Look at that activity difference.